Okay, so I hope my screen is visible to all of you. So as I had mentioned in the last class, that in today's class I will be talking about fragmentation and reassembly of datagrams. Okay, so we know how, so this is an IPv4 datagram. Okay, so how does an IPv4 datagram look like? This is what we have already studied, that we do have the version number here, the header length, the type of data, the time to live field, etc. Okay, so I'm not going again on this same slide because you already know what it is about. But the most important thing that you always have to remember is that we do have a 20 byte of IP header, right? So this total overhead, including TCP, is 40 bytes. But when it comes to an IP datagram, the IP overhead is about 20 bytes here. Okay. So let's get to fragmentation and reassembly. Okay. So why do we need this fragmentation? When we were looking at the application layer, we had started with the fact that it is very difficult to send an entire data over the link, and it also takes up a lot of resources. So what do we do in general is that we break the data into small packets. Okay. Now, that was over the link. What happens? That's what we had discussed. Today, what we are going to discuss is in terms of the network layer protocol as to what happens there. And what we have learned by now is that we divide, the message from the application layer basically gets added up with some more information as a header at the transport layer, becomes a segment, and then when it comes to the network layer, it becomes a datagram with some added information in its header. Okay. Now this transfer of datagram from a host to another, so that also happens in fragments because the datagram size may become quite large. So the maximum transfer size or the maximum transfer unit, which is known as MTU, that is the largest possible link level frame, and it is given out or it is decided depending upon the different type of link which is between the hosts. Okay, so every link type between hosts will have its own MTU. All right, so depending upon the MTU, the datagram will be divided as per the MTU size, and then it will be transferred over the medium. So this is how it is happening. So as you can see here, there's one datagram here. So this within this link from one host to another, suppose the MTU size is quite large and it could be sent in the same in this single MTU, in the way of this single MTU. Now, once it comes to the, or it has to move through another link, then the MTU size is smaller. So what we do is, so the input to this router is basically one large datagram, and the output from this router is three small datagrams. So that is when we do the fragmentation. That means you are fragmenting the datagram into three different MTUs, smaller datagrams, and it reaches the host as three small datagrams. Now at the host, of course, you have to reassemble these three smaller datagrams to get the actual datagram, right? So that's the concept of fragmentation and reassembly. That is, you fragment the datagram and then you reassemble it at the host side, receiver host side. Okay. Now, when you are fragmenting something, if you remember when we were talking about segments in TCP, right? Sorry, not in TCP, in reliable data transfer. Then we had given sequence numbers to the different packets so that we can actually find out that which one comes after which, so that we can have a in order reception at the receiver side, right? So similarly, when it comes to the datagrams, when we are doing a fragmentation, and we want to have a reassembly, so there should be some kind of a sequencing. Okay, so IP header bits are used to identify and order the fragments. Okay, so we will see how this ordering and all is done. So let's go to that. Okay, so suppose this is a datagram. Okay, the length of this datagram is 4000 byte, and we have these three fields. Okay, ID, fragmentation flag, and offset. Okay, so what are these fields going to tell us about? Okay, so the ID field is not relevant to this fragmentation and reassembly. It what we are going to be concerned about is the length, the fragmentation flag, and the offset flag. Okay, so let us assume. So this is an example. Let us assume that the MTU for the link is about 1500 bytes, and the datagram size is 4000 byte. Okay, so now you have to divide this original datagram into fragments of 1500 bytes. Okay, so that's what is being done here, and you have a fragmentation flag. So fragmentation flag is going to tell that whether there is a next fragment or not. If the fragmentation flag is set as 1, that means there is a fragment of this same datagram which is going to be incoming soon. If it is 0, that means there's no further fragments of the given datagram. Okay, and offset is given by that how many offset is given by the first one is 0, and it is given by that how numbered as the bits. Okay, so you divide by 8 and then you get the offset number. Okay, so now here, if you remember that we had considered that 20 bytes of IP header, that overhead is there always. So when if the MTU length is 1500 bytes, so you have to keep the 20 bytes for IP header, and the rest of it can be the data field. Okay, so that's what is happening here. Okay, all right. So now offset will be, see, when you are considering the offset, that means you have to see that what is the sequence in the data string that is coming, right? So that is why we divide by 8 with the amount of bytes in the data field that will be there, and similarly you will get the offset values. Okay, now, okay, I hope that this part is clear. So the fragmentation and reassembly is actually quite an important concept. Okay, so what you have to do is that you will have some examples in Kuros and Ross's book, some numerical examples. So please go through the numerical examples. Okay, I'll try to take some class in which we will show you that how, or we will just do some numericals. I'll try to do that given if the time permits. But anyways, for a self-study session, I will suggest you to go through the fragmentation and reassembly numericals. Okay, because most of the times students they generally forget this 20 byte header part, or the offset they divide with the entire thing. So those things can happen. So if you practice, it will be better. Anyways, all right, let's move forward. So what we have studied so far over the network layer protocol. Okay, so we know that what we are doing over here is that we are trying to send datagrams from one host to another host. Okay, just that is the task. Now, logically, if we are going to do that, we have to move through all the other routers present in the network, because the routers also have network layer functionality. They are going to say that what should be the next interface, what should be the next um, interface for the path of belonging to this source and destination pair. Okay, so apart from this, what we have studied is that we have found out that how the IP addressing is done, IPv4, IPv6 we have studied, and we have also seen the functionalities within a router. Okay, we had just started a little bit on routing algorithm, but because that was a part of control plane, we have stopped it a little bit. We are trying to finish the data plane part today, and then again from tomorrow's class, we will start fully on the control plane part. Okay, so this part was remaining, so I am teaching this part today. So this is what we have studied, right? So it's like one datagram. It's just moving from the source host to the destination host. Okay. Now what we have studied is that there are two network layer key network layer functions. One is routing and another is forwarding. So forwarding will be like moving the packet from router's input side to the corresponding output side, or if we have to be very correct, it will be the corresponding interface. Okay, and routing basically is determining the route from the source to the destination using different types of routing algorithms. So this is what happens. So there is a packet that is arriving with a given header value. Now, depending upon what's the header value, now, as of now, whatever we have studied that this header value that we are looking at is the destination host's IP address. Okay. With that, we are basically finding out that what is the corresponding interface. Okay. Now, we will see in this class itself, we will see that it may not necessarily be the the destination host's IP address. Okay. Anyways, for now, what we have studied is that we check the destination host's IP address in this header field of the packet. According to this value, we get from the routing algorithm, we get the end-to-end path, and with this information, we actually find out that what should be the corresponding output link from the forwarding table. So now, there's another important setup or third important function that comes in some of the network architectures. Okay, so these architectures are ATM, frame relay, and X25. Okay, so we have not studied any one of these as of now, but I think I had mentioned about ATM in one of the classes, that is asynchronous transfer mode, which is nothing but a combination or a kind of a logical combination of a packet switched as well as a circuit switched network. Okay, so I will get to this ATM once I finish the entire the entire TCP/IP layer, because it's a entirely different kind of network architecture. But if you are interested, just go ahead and look at ATM. What is ATM? All right. Just because in this slide I am just mentioning that ATMs are actually a kind of network architecture, and they have this important function, which is a connection setup. If you remember, when we were looking at circuit switched networks, then there was a particular step where the connection had to be set up between the source and the destination. Okay, so when it comes to these kind of networks which are actually using the properties of circuit switching, in that case, one of the important tasks would be, or one of the important functions for the network layer will be connection setup. Okay, so what exactly happens in this step? Before the datagrams flow to end hosts and intervening routers, they establish a virtual connection. Okay, so it's not only that the connection is done between a source and a destination. The intermediate routers also get involved in this virtual connection. Okay, because we are talking from network layer point of view. So this, I think, you are already aware of quite nicely that the connection service, the difference between the connection service between network layer and transport layer is that the connection setup for network layer has to be between different hosts, whether it's a source, destination, or different routers in between. But in case of transport layer, it has to be between two processes. Okay. Now, okay. So the question that is given here is that what kind of service model for channel transporting datagrams from sender to receiver? Okay, so that means what are the features that should be there for the channel if uh, some data has to be transferred from the sender to the receiver? Okay, and depending upon the network layer, what should be the network layer service model? So I think we have already done that in the previous classes that um, for individual datagrams, it should be that it should give out guaranteed delivery. It should have, or at least it should have the delivery within some amount of or some delay bound. Um, as for the flow of the datagrams, there should be in order delivery of the datagrams. There should be at least some guaranteed minimum bandwidth to flow, and there should be restrictions on changes in interpacket spacing. So these are some of the requirements that a network service model can provide. Okay, not necessarily all of these are provided all the time. It depends on what is the service model that you're looking at. Depending upon that, the services are provided. Okay, so these are some of the network layer service model. So this is based totally on ATM. I think I had talked about something like this, or I don't exactly remember right now. I think I had talked about this in the beginning of network layer classes, where I had talked about that internet basically uses best of both service, where there is no guarantee whatsoever for either bandwidth, packet loss, in order delivery, or even timing, and even for congestion. Okay, so internet which uses packet switching, it generally does not give any kind of guarantees oops, or service guarantees. Whereas when it comes to ATM, okay, it has different service models, that is constant bit rate, variable bit rate, etc. So those services, they have their own requirements, and these guarantees have to be provided by the service provider. Okay. So these were the things. So because ATM has not been taught yet, so we are not looking at it right now. But I would suggest you to just go take a look at what is ATM, so that you know this does not become confusing. Because if we have to get into ATM, you will see that we have to check out from end to end. Okay, from the bottom layer to the top layer again, and that will be very different from what we are doing currently. So let's first see that how in our TCP/IP layering, how the protocols are working. Then we will go ahead and check out ATM. Okay? Now, um, we were talking about that when it comes to special networks like ATM, frame relay, etc. In those networks, we give out or we use certain properties of circuit switching, or we try to use certain properties of circuit switching. Whereas when it comes to our internet, we are using only packet switching. Okay, so you can see that we have connection oriented services and we can have connection less service also. Okay. So connection less service is of course the kind of network that we are using over the internet, and that is known as the datagram network, where the network layer is a connectionless service. Whereas when it comes to connection oriented services, we call it as virtual circuit network. Okay, that means when we want a connection oriented service over the network layer, then virtual circuit network provides such a connection oriented service. and we are going to see what is a virtual circuit network. Okay. Now, before that, there's this last point here that these two datagram circuits and virtual circuits, they are analogous to TCP/UDP's connection-oriented and connection-less transport-layer services. Okay, but only the difference between the TCP/UDP connection-oriented and connection-less services and this datagram and virtual circuit services is that here the services are from, in TCP/UDP, the services are from host to host. No, sorry. In datagram and virtual circuits, the services are from host to host. In TCP and UDP, the connections or the services are from one process to another process. Okay. So there's no choice here. The network provides either the connection-oriented service or the connection-less service, and implementation is over the network core. Okay. So let's start with virtual circuits. What are virtual circuits? So as I mentioned you, or as in this slide we have already mentioned earlier, that in some circuits, or in some kind of networks, there is a third very important step apart from routing and forwarding, and that is connection setup. Connection setup will be required for those kind of networks where we are using some way of circuit switching or some logical way of circuit switching. Okay. So virtual circuits is a way in which we are virtually trying to use the features of circuit switching in the network. Okay. So what happens here? The source to destination path behaves much like a telephone circuit, performance wise, as well as depending upon the or as well as the network actions along the source to destination path. Okay. So what is done here, as in circuit switch networks, you will have a call setup phase or call tear down phase for each call before the data can flow. Okay. Now we have a virtual circuit identifier that will be carried out by each packet. Okay, which is not the destination host address. Okay. So, and what happens? Every router will have or will maintain the source to destination path. That means this is a stateful protocol. Every router will maintain the state of the source to destination path for each passing connection. And when we are trying to set up the connection between the source and the destination, then the link and the router resources, for example, bandwidth, buffers, etc., they may be allocated to the virtual circuit. Okay, this is because, see, here we are actually using this in case of those kind of networks where you actually want to guarantee some types of services to your customers. So if you want to guarantee something, definitely you have to dedicate some resources for that. So that is what is done in this case. All right. So what's done? So let's see the implementation of virtual circuits. Okay. So a virtual circuit consists of three things. One is, of course, the path from the source to the destination. Then you have the virtual circuit number. Okay. So what is this virtual circuit number? It is nothing but a number that is given for each link along the path. Okay, we will see examples as to how it helps. And you want to have entries in the forwarding tables, okay, in the routers that you have along the path of the source and the destination. Okay, so what happens when you identify each link with the help of a virtual circuit identifier or a virtual circuit number? Then for each packet, instead of putting the destination address, we put the virtual circuit number. So your header size will become smaller. Okay, you don't have to put the entire IPv4 address on that. You just have to put the virtual circuit number on that, and that will be an easy identifier. Okay, now you can of course change the virtual circuit number on each link and then update the same information on the forwarding table. So that's how it looks like. Okay, so you put each interface you identify as with a given virtual circuit number. Okay, so this virtual circuit number is actually advertised to the neighboring hosts. Okay, so what happens here? So in the forwarding table, at each router in the forwarding table, there is an information that is for a packet which is coming with a particular virtual circuit number. So take a look at this. For interface number 1, in the figure you can see that there's a router with 3 interfaces, 1, 2 and 3. Now for incoming interface 1 for this router, this is the forwarding table of this particular router. So now in this one, what it is writing is that in the incoming interface 1, if the incoming virtual circuit number is 12, that means the corresponding outgoing interface is 3 and the outgoing virtual circuit number for this interface is 22. So with this, what will happen? Any packet that has arrived here from interface 1, if it is coming from this particular host, then it will have a virtual circuit number in its header field, which is 12. So when the packet arrives at this router, it will check in the virtual circuit forwarding table or VP forwarding table that what should be its corresponding output interface. Right. So it will check in the forwarding table. It will find this entry where these two things will match. That is incoming interface and the incoming virtual circuit number. Once they match, then the corresponding output, that is outgoing interface and outgoing virtual circuit number. That's what the packet has to follow now. So the packet will now go to the third outgoing interface, and in its header field, the virtual circuit number will be changed to 22 because it has been already advertised by the next router that if there is any packet that comes through this interface, then it will be numbered as 22. Okay, so this exchange of information keeps happening, and with that information, with the help of virtual circuit numbers, or you can also call it virtual circuit identifier. So with these identifiers, we try to reduce the amount of processing that is done over each packet. Okay, so the amount of time for processing gets reduced, and it further guarantees that whatever guarantee or whatever performance guarantee you are trying to give to your customers, you will be able to, or you are trying your best to provide that. Okay, you will be able to guarantee those features to your customers. Also, additionally, as I had already mentioned, that the virtual circuit routers, they maintain the connection state information. Okay, that means whether the connection is still live or not. So that information is also available. Okay. So how does the virtual circuit work out? Okay. So the signaling protocols that I used to basically set up the virtual circuits. So they are used to set up and maintain set up the circuit, maintain the virtual circuit, and then tear down the virtual circuit. Okay, it is used mostly in these kind of networks, as I've already mentioned, ATM, frame relay, and X25. Okay, so it is. I wouldn't say that it is entirely wrong that it is not used in today's internet. Okay, there are still certain very special kinds of architectures where we use ATMs and frame relays, etc. And there are many different ways in which this concept of virtual circuits is used in case of the different network architectures. Okay, as such, virtual circuits is not used in our internet. Okay, so but this concept is very much important for any architecture, any different kind of network architecture that we might use. Okay? Now let's see how this virtual circuit works out. So we are basically looking at a logical connection from network layer of one host to the network layer of another host, right? So apart from routing and forwarding, the third important step for such kind of network is connection setup. So first thing is that there should be an initiation of the call, or since this is written as a call because it is trying to show you the parallelism between a telephone network and this kind of a virtual circuit network. It is just simply that it is initiating a circuit between the host and the so between the source host and the destination host. Okay, so once this call for setting up the connection is initiated, then it will be, of course, there will be an incoming call, kind of a request that is arriving at the destination host. Okay. So once the destination host accepts this, that yes, this is okay, that we can actually set up a connection between the source and this destination, after that only the call gets connected, or the circuit gets connected. And then the data flow begins, and of course the reception of data happens. And this stage is known as the maintenance stage. Okay. So until step 4, it was a setup phase. Then 5 and 6, that is a maintenance stage. Okay, so how does it happen? Okay. Now, in case of datagram networks, this is completely different. Let me just go back once again. Just a second. It's not doing that. Okay. So, what would happen here, that when there is a connection to be set up, then a request will be sent from the source host to the destination host. When the destination host says yes to that connection, then through that given path, the call will be connected, or the circuit will be connected between the source host and the destination host. Okay. Once this path is set up, once this connection is set up, then the corresponding data transfer will happen, and this is the maintenance stage, or maintain stage. Okay. After this, once the data transfer is done, then the connection will be teared down. Okay. Now that was virtual circuit networks. Now this is datagram networks, which is the network that we are using in our day-to-day life over the internet. So here we do not need any kind of call setup or any kind of connection setup. There's no end-to-end connections. Simply packets are getting forwarded from source to the destination as and when the resources are available. Okay. Now you might ask the question that for the previous, I don't know why from here it is not going back. Just a second. Okay. So you might ask that, when is this resource getting allocated and all? We had talked about this in the last, in the previous slides. Okay. So the thing is that here, as you can see, that whenever you are setting up the connection, and when the after the host actually is the destination host actually agrees to set up the connection, while doing that itself, the resources are logged for this connection so that the communication can take place. Okay. So this is the datagram forwarding table. We have already learned about this. So this is just a small recap of what we were talking about in our last classes. About we have already studied that you just check the address range in the forwarding table. So we had learned about longest prefix matching. We had learned about we check the address range, or in longest prefix matching we check the longest prefix match, and then we find out that what should be the corresponding output link. Okay, so but the only problem is that if there are too many IP addresses, your forwarding table size is going to be too large, and the checking of addresses also becomes too difficult. Okay, so that's what is there. So we have already studied this part. This is I think I will not go ahead with the same thing again. What we are going to do now is something very interesting. Okay, let's see. Is the new PPT visible to all of you?
Yes, ma'am.
Okay, okay. So we are going to start with the last part today. That means the last part of the data plane that we were talking about. Okay. So if you remember, we were talking about that when you are forwarding a packet from one input port to an output port in a router, in general, we are basically looking at the destination IP address and then doing the forwarding. Okay? And while doing that, I also mentioned that it may not always happen, or it may not be the case always. Okay? So you can forward the data according to certain features which are other than the destination field. Okay, so for example, that you are simply sending or you are simply checking that okay, all the IPv4 routers may be IPv4 packets may go through this interface, and then it can further go ahead to any other router. Okay, so you will just check a very small field of the IP header. So this kind of forwarding where you are just not checking the only the destination address, you can check any other field, okay, and then take an action on the particular packet. That kind of technique, that phenomenon is known as generalized forwarding. Okay, so it is basically match plus action. That means you match the value with some value in the forwarding table of the router, and then take the appropriate action. Okay, so so this is what I have already told you. Now, when it comes to destination-based forwarding, that's what we were thinking, or we have already studied up to now, that we just forward the packets based on the destination IP address. Generalized forwarding is that you can take either some other field or a combination of different header fields and determine that what should be the corresponding action on the packet. The action can be different, like you can drop the packet, you can copy the packet and keep a copy of the packet and then transfer it, you can modify the packet, you can keep a log of the packet, and many other things. Okay, so this is known as generalized forwarding, right? Now the next part is flow table abstraction. So what is flow? Flow is defined by the header field values. Okay, so what are these header field values? That is in-link value, network value, transport layer fields. Okay, so what's the input link? What's the network layer fields? What's the transport layer fields? And generalized forwarding gives you simple packet handling rules. Okay, so what you do in generalized forwarding, you simply match the pattern of values in packet header fields, and then you take the corresponding action, which can be either you drop the packet, forward, modify, etc. Okay, so the router's flow table actually defines what should be the match and action rules. Okay, so whatever field values you are checking, that will be there in this part, that match column, and then according to that, the corresponding action will be taken on the data. So, why is this generalized forwarding done? It can be done to, give some priority, or you can just put some priority to disambiguate overlapping patterns. And you can put counters as, what is the number of bytes, what is the number of packets that is being forwarded, etc. Okay, so here I don't know whether you are able to see all the interfaces of the router. Anyways, it has 4 interfaces, 1, 2, 3, and 4. And you can see that this is basically nothing but just an example of what can be the match and action values correspondingly in a flow table. Okay, so let's see the match value here is given as the source and destination address only. Okay, so suppose you match with the source destination fields, and then correspondingly this is the action that is being taken, that is the source destination pair matches this one. Then you have the corresponding value or the corresponding action that you have to take is forward to interface 2. If the second one is true, that means if the source and destination pair is this, then the packet will be dropped. Otherwise, it will be sent to the controller. Okay. So this is another concept that we have, which is known as open flow. So what we have is we have match action as well as stats field. So match action means you can match these header fields to match. Okay, you have the input port or the ingress port, you have the source, destination, MAC address, Ethernet type, VLAN, ID, VLAN priority, etc. This is the network layer part. Okay, IP source, IP destination, etc. And then you have the transport layer part. Okay, so these are the different header fields that you can match. Then you have the action field where you can perform these actions corresponding to the matching pair that you are basically putting in the match column. So you can either forward packet, you can drop the packet, you can modify the fields, or you can encapsulate and forward to controller. And stats means you are simply keeping the statistics of, what is the number of packets, what is the number of bytes, etc. So these are the counters that are basically kept here. So these are some examples of open flow based, tables, or what you can do exactly when it comes to open flow. So in destination based forwarding, you can see that. See, this is the IP destination, and this is the corresponding action field. Okay, so for this particular IP address, that is 51.6.0.8, the action is that it should be forwarded to router with output port, forwarded to the router's output port 6. So this is destination based forwarding, this will happen. Now there's one more advantage, or one more usage, basically one more usage of this open flow, which is firewall. Okay, so what do we do, or how do we do this? That you if there is a TCP destination port of 22 in packet whose TCP destination port is 22, the action is you drop the packet. Okay, so that means, so here this is what is given here, the block or do not forward all the datagrams that are destined to TCP port 22. Okay, this is basically an SSH port number. So this is how you do a match and action pair. And this is a part of the generalized forwarding, where you are simply just not doing a destination based forwarding. There are other use cases also, or usages also, that you are doing. Okay, now this is like firewall, where you are blocking one packet, one kind of packet with a destination port, with a given destination port number, whereas in the other one you have that you do not block or do not forward, sorry, you block the packets, and here you are not checking the TCP destination address, you are simply checking that whatever is coming from a particular source, That means if you find out that in your network there is an attacker, and you somehow find out the source IP address of that particular attacker, right? Once you get to know that, you can keep this, that if there is a packet with this particular source address, in that case you drop those packets because it is congesting the network. Okay, so this is how you provide certain use cases. This is also another one, that is this one. I think in the next chapter it will make more sense, but anyways, this is given as a layer 2 destination based forwarding, that is link layer based or destination based forwarding. So we will see in the next chapter that layer 2 destination based forwarding means that you will have some kind of an identification depending upon your layer 2 based destination address, which is called as MAC address. So you can see that if the MAC destination address is given as this, then the packet should be forwarded to particular port number 3. So this destination based forwarding depends upon layer 2. This we will get again in next chapter. Now let's see about open flow abstraction. Okay, so how does it help? So this match plus action, this helps in this abstraction basically helps in unifying different kinds of devices. Okay. So excuse me. So in router, what you do? Okay, so the match would be in the router that you can have a longest destination IP prefix match, and correspondingly, the action that you can take is you forward it through a particular link. Okay, so that is in the router you can do that. In the switch is a layer 2 device. Okay, so switch, you can check the destination MAC address, and then you can forward. The action would be that you either forward the packet or you flood the packet over the given subnet. Another is, of course, firewall. We have already seen the examples that you first find out the match. The match can be based on either the IP address or the TCP or UDP port numbers. And depending upon that, you take an action of either permitting the packet or denying the packet. And the fourth one is NAT. Okay, so what do we do in NAT? What can be the match and action pair? That you match the IP address and port number, and the action that you take, we know that if it comes to NAT, then we have to either rewrite the address and the port number. Okay, so this is an example, and I think I don't have much time. Let me just get to this. Just take a look at the example here. So this is simply, there's one host, and then the datagrams from host H5 and H6, H5 and H6, they should be sent to a host H3 or host H4 via these switches S1 and S2. Okay, so if this comes to picture, you can have these match and action pairs, and then correspondingly you can take a decision. Okay, when you are setting the packets. So this is what happens here. If the source is 10.3.star, so you can see host H6 is 10.3.0.6, host H5 is 10.3.0.5. Okay, so if the source destination and the destination addresses correspondingly for H3 and H4 is 10.2.0.3 and 0.4. So if the source destination pair matching is this, then the action is that you forward through interface 3. Okay, so this is what's happening here, and then at this particular router, that is S1, what's happening is that you first see that if there is a packet that is arriving through port 1 or ingress port or interface 1, and the IP and source and destination address is given by this prefix, in that case the action that is taken is that forward the packet through interface 4 or into port 4. output port 4. And similarly for S2 also the same thing will happen, in that because it is now connected to the two destination hosts H3 and H4. So it has to check that first thing will be the ingress port. Of course, the ingress port is going to be 2 here. So for both the cases, ingress port is 2, but the destinations are different. If it is 10.2.0.3, then forward through interface 3, which will send to host H3. And if the IP destination is 10.2.0.4, then it is forwarded through interface 4 to reach the destination host 4. Okay, so I think I'll stop the class here. And if you have any questions, you can ask. Otherwise, the class is over. I'll take up the rest of this part as